The number of connected devices rapidly increases, producing extensive amounts of data. The constant data stream puts a heavy load on the cloud server that processes it, and a significant strain on the network to deliver it to and from the cloud. To address this issue, the concept of edge computing emerged, suggesting moving the data computation closer, or directly to where it is produced, to where we, humans, interact with devices. The devices are located far from the central cloud, on the edge of the network. They are pieces of equipment we refer to as Internet of Things devices, that can range from low-power sensors to high-performance industrial equipment. These devices were built for some purpose, to perform a specific function, and they just happen to have the computing capacity on them. If computation is offloaded to them, only important events will be sent to the cloud, enabling faster communication with a large number of devices. However, there is still a lack of widely applicable, secure, and smart edge solutions. To address this challenge, the FRACTAL project has created a computing node that is a building block of the scalable Internet of Things. This node can be installed on bigger or smaller systems within IoT. The uniqueness of the node is the cognitivity and fractality features, which are inspired by nature and biological beings. Human brains are cognitive because they think, reason, interact, and adapt to the environment. They also communicate with other brains, able to learn from their experiences. In the FRACTAL node, cognitive processes are replicated using modern technology, like cognitive computing and machine learning. At the same time, through the communication processes between the nodes, they exchange experiences and learn from each other. Another main quality is fractality. It happens when an irregular geometrical structure replicates itself in multiple different scales. No matter if we zoom in or out, we will always find the same shape as we saw previously.
Now imagine an IoT system as a big and chaotic world where lots of devices are connected and gather data. The whole system is cognitive, because it is dynamically connected, processes data, learns from its context, and adapts to changes. Then, let's zoom into a smaller part of the system, like a smart car. The car is also cognitive because it senses the environment, learns and adapts. It also communicates with other cars and systems within the same IoT network. Then, we can zoom even further, into the wheel of the car. The wheel is also cognitive, as it learns from the data of its own sensors. It is connected to other wheels in the car and possibly other devices.
For such a smart system to exist, there is a need for a reliable computing node that can function on a big and small scale. The FRACTAL project fulfills this need by creating the technology system and architecture that can be used and will deliver the same benefits on any scale. Let's see how this system has been designed.
From a high-level point of view, the FRACTAL system can be seen as a layered architecture with 3 layers. A node layer represents an infrastructure of the computing nodes, the edge node or cloud node. It includes the hardware, such as platforms and accelerators for AI. It also includes low-level software, such as operating systems and drivers. The cloud node is optional and supports the edge nodes in certain functionalities, such as training of machine learning models. Over the node layer, there is an orchestration layer. It is responsible for the orchestration of the components and services of the system, as well as for the management of the distributed system. Finally, the application layer includes the business logic for the applications. On this layer, specific functionalities are built as microservices in containers and deployed over the nodes.
This system can be implemented on a different scale, and its main features include security, safety, low power, reliability, adaptability, openness, context awareness, and fractality. To enable these characteristics, the fractal system has been designed as a modular system, which consists of different technology components that have been developed during the project. Here we can see the big picture and the architecture of the fractal system. We can navigate it to show the various technology components developed in fractal. For different applications, a different set of components can be selected depending on the characteristics of the application. To demonstrate this component selection process, the fractal configurator has been designed. First, the desired features of a use case must be specified and selected. Then, the configurator presents the corresponding system layout with only the required components for this use case.
To verify and validate the technology, the fractal system has been applied to 8 different industry use cases. The first use case has been led by Prointech and consists of 2 solutions. One of them uses drones to perform a near real-time piloted technical inspection of hard-to-reach components in buildings, bridges, and other civil structures to monitor and detect hazard. Another one focuses on monitoring safety conditions during construction processes. The fractal node processes raw data coming from sensors on workers, machinery, and construction site, sending the key insights to the IoT platform, which register possible dangers and sound proximity alarms. Use case 2, led by AVL, addresses the challenge of an increasing number of parameters and calibration targets for the control system of battery electric vehicles. With Fractal, we are able to use reinforcement learning techniques to design appropriate control strategies, which reduces the development efforts. The third use case was led by ACP. In this use case, based on the RISC-V ecosystem, a low-cost, battery-operated smart meter prototype was developed. The prototype can read analog meters by taking a picture of the meter, analyzing it directly on the edge, and transmitting it over the cellular wireless network. The proposed solution achieves a battery lifetime of 5+ years, and manages to establish a wireless connection in areas with poor signal-to-noise ratios, thanks to an extended coverage protocol, NB-IoT. In the use case 4, led by Siemens, a generic control system was created, with potential applications in predictive maintenance, autonomous robot guidance, and many others. The new system offers low-latency inference at the edge, in combination with cloud-based training. In the use case 5, CAF signaling applied the fractal approach to improve autonomous train operations. Real-time and safety-critical AI-powered system ensures such functions as accurate stopping and safe passenger transfer of driverless trains. In the use case 6, iTech, together with Univac, integrated the fractal cognitive node into a smart mobile totem. This will help to promote intelligent interaction with different people, guaranteeing low power and a high level of engagement. Use case 7 was led by virtual vehicle. Adaptation of an autonomous robot for advanced driving assistance systems testing utilizes the open-source components from Fractal, which enable the execution of safety-critical vehicle functions alongside machine learning-based applications. Finally, in the use case 8, BWIN applied the Fractal technology in a warehouse with intelligent autonomous shuttles. Cognitive capabilities on the edge and swarm intelligence improve availability, throughput, and safety.
Fractal cognitive edge nodes make products smarter, more interconnected, interdependent, collaborative, and autonomous by bringing computing closer to the devices and users and allowing more efficient use of data and energy. This improves sustainability in all of its aspects: economic, environmental, and social. Running applications with distributed data on the Fractal edge nodes reduces the network's bandwidth and data center usage, which reduces energy consumption and costs. This makes it more difficult to experience leaks of large datasets, which has a big social and economic impact on the security and privacy of individuals. Low-end fractal edge nodes based on open-source technologies provide a way to lower the entrance bar to business for hardware devices by reducing investment needs. The safety and adaptability of the fractal edge nodes make the connected devices more reliable and resilient. This will expand the life cycle of the manufactured products, reducing their associated environmental impact, even if the performance requirements and/or business models change. The FRACTAL project has been a key project in solving edge computing challenges in the European Union, and it has created extensive accessible know-how for the digital decade.